Okay, let us continue our discussion further. So let's start with a quick recap. Okay. So we started treating psi, which was the field obeying Schrodinger equation, as a classical field, and the Schrodinger equation as a classical equation of motion. Okay, so that's what we did. So we regard psi as a classical field okay, which was the, and regard your Schrodinger equation as a classical equation of motion. Okay. And then we wrote down the action of the system, which will give Schrodinger equation as the equations of motion. And our action was this. So you get S is equal to dt d cube x psi star, okay, and we had in this round brackets the entire Schrodinger equation, the left hand side of the Schrodinger equation. T over delta t minus the Hamiltonian of single particle quantum mechanics. Okay, sorry. T. Okay, that's what we did. And remember, the Hamiltonian was this minus h bar square over 2m, where m is the mass of, well, let's not say anything now, because we have changed the description. So I'll be confusing you by saying mass here plus v of x. Okay, so we had a potential in the problem. Okay, and then we derived equations of motion using delta s equal to 0, and that treating psi star and psi as independent variables, we found that the equation of motion was what we wanted. I mean, that's not surprising. That's how we constructed things. Okay, and let me say here, this quantity in square brackets, okay, I forgot to put a bracket here. The quantity within square brackets is called Lagrangian density. Okay, it's denoted by curly L. Okay, Lagrangian density. Okay, that's what you have within the square brackets. Then if you integrate the Lagrangian density over all of space, then you get the Lagrangian. Okay, that's your Lagrangian. Okay, and when you integrate the Lagrangian over time, you get the action. Okay, as Let me write it a little bit nicely. Easier action. Okay. Now you see here, S is actually a functional of psi. You see, these are integration variables, so dt and d cube x. So you are integrating over the entire, all times and all space. So that's gone anyway. S does not depend on what t is and what x is, because that's integration variables. It depends on psi and psi star. Okay, so if you specify a field configuration, meaning if you take the entire all space and tell what is the value of psi at each point of time. Okay, so at each point in space and time, you say how big psi is. I mean, in this case it's complex, so you have to tell both psi, real part of psi and complex part of psi, but you have to tell at each point and at all times. If you specify that, okay, then you can calculate the action. If this changes, you get a different value of the action. Okay, so S is dependent on this entire specification of psi. What is psi throughout? Okay, action depends on it. So S action is a functional of psi. So that's what we are making more specific here. We'll come back to functionals in more detail later, but for now we make this note. Okay, and we also wrote that psi as a linear sum over the wave functions of the Hamiltonian. Okay, this small h, because the wave functions form a complete set, we can write it. So I wrote earlier a n of t u n of x. Okay, and of course, as I mentioned last time, this is a system of infinite degrees of freedom, because you have n runs from 1 to infinity. Okay, you have to specify infinite number of a's to specify psi. Okay, that's good. And we also said that a and r, the generalized coordinates that describe this system. So they are the dynamical variables of your problem. Okay, now if a's are the dynamical variables of my problem, I would like to write down my Lagrangian, my action, Hamiltonian, everything in terms of these a's. Okay, and that's what I'm going to do now. Okay, so I will use this decomposition of psi and express everything in terms of the dynamical variables a. So let's go to the next slide. Yes. Okay, good. So let me write it down here again. So your psi, let's go to Lagrangian. The Lagrangian is integral d cube x psi star. Okay, here. So d cube x psi star and this piece. Okay, so I'm going to substitute in this here, in this part, this decomposition of psi. That's what I'm going to do now. So here is psi star, but psi star is um, instead of n, I'm writing m. Sorry. So what is psi star? Psi star is m am of t m of x, but it's psi star, so there has to be complex conjugation here. times, so that part I have taken care of, psi star, and then in the bracket we have IH bar del psi over del t. Okay, time dependence is only in the APs. Now I am writing psi, not psi star. Okay, del psi over del t. So UM will remain outside, and you will have del A n t over del t. Okay, let me try to write it a little neatly. It looks horrible. I will use a different index n. I will not use m. Del A n t over del t, and you have u n of x. Okay, that is correct. And I should sum over n. Okay, that is IH bar del psi over del t. Then I have minus h bar square over 2m. Okay, did I make a mistake somewhere? No, minus h. Okay, minus h. So let me put a bracket here, it will be easier. Minus h bar square over 2m. Then we have sorry, I don't need to do that. Sorry. Okay, so minus we have, let's go back, h acting on psi, but psi I have expressed using a and u. U are the wave functions of the Hamiltonian h, okay, with eigenvalues en. So when h acts on psi, it will act on un, it will give us en un, and of course a is already there. So what I will get is this. Let me write down en. You will have un, and you already had an of t. Okay, that is what we should get, and everything looks fine to me. Okay, let's collect some terms. Yeah. So first of all, note that del A t over del t same as dA over dt. Okay, there is no distinction because A is a function of t only there. It doesn't have some other dependence. I mean, you can look at this in more detail. It's del over del t plus del over del x, okay, into dx over dt. So that's what it is. But if you put a function a which depends only on time, this piece is 0, right? Because it's a partial derivative of a thing which depends only on t. So this is gone, and that it's clear that what I'm saying is correct. So you get the following. You get summation over n, summation over m. Let me collect un and ums. So you get integral d cube x star of x un of x, okay, times IH bar d over dt, which is a n dot, okay, I will use a shorthand notation, minus en an. That is correct. Okay, let me not suppress time here. Okay, good. Now I can use the fact that these wave functions are orthonormal. Okay, I can choose them to be orthonormal because they are eigenfunctions of Hermitian operator, the Hamiltonian of the single particle quantum mechanics. So, which means that if they are orthonormal, then it means that if you write this x u n of x, then this is just delta m n. So, when m and n are same, equal, meaning you have the same function in here, then you get 1. If m and n are different, then because they are orthogonal, you get 0. Okay, delta m n will be 0. So, that is the condition we have, which if I put here. So, if I replace this piece with delta m n, is something missing, something is missing, this piece is missing, yeah, this one is missing. I should write here a m star of t, okay, and this crosses, yeah, it is there, I can remove it, but it is okay. So, this gives you a delta m n. Now, when you are summing over all m, okay, then it will, so what you get here is summation over m delta m n, and you have a m star of t, okay, another factor does not depend on m. So, it's fine up to here, okay, and when I sum it, it will pick up a n star. Okay. So, I get summation over n a n star, okay, and then I h bar a n okay, let me write d a n over d t. There is no need for putting a dot, but it is fine. E n a n t. So, that is what we get for the Lagrangian, and that is good. So, we wanted to write our Lagrangian using only the dynamical variables, and which we have achieved now. We have only the a n's and a n stars. Okay, so, that is fine. Now, I would like to construct the Hamiltonian, and if you recall how Hamiltonian is related to the Lagrangian, it is p q dot minus L. So, I have to construct first the momentum conjugate to the dynamical variables A. Okay, so, that is what I am going to do. Okay, so, let us construct momentum conjugate to a n of t. And how do you get that? So, if I define that conjugate momentum to be p n, okay, then p n will be del L, the partial derivative of the Lagrangian with respect to q dot. And what is q here? It is a n. So, it is a n dot of t. Good. And what is that? If I take this Lagrangian here and take a partial derivative with respect to a dot, and this is the a dot, I get I h bar a n star, and this term anyway does not contribute because there is no a dot involved in here. So, I get I h bar a n star of t. So, that is the momentum conjugate to a n. Now, I can construct the Hamiltonian, that is straightforward. So, the Hamiltonian of this system now, I am not talking about the Hamiltonian of single particle quantum mechanics, I am talking about the Hamiltonian of this system, and that I will write as capital H. Okay. So, how do I construct the Hamiltonian? Hamiltonian is PQ dot minus L, and you sum over all the coordinates. So you have summation over n, Pn, and what is Q? Q is your A. Okay, looking very ugly. PQ dot minus the Lagrangian. Okay, and what did we find Pn to be? Pn was IH bar An star. So let's write that. IH bar An star An dot, I'm suppressing T now, summation L minus, let's go back and see what the Lagrangian was. So this is IH bar An star An dot, IH bar An star An dot. Okay, this is the same thing here. Let us write anyway. IH bar An star An dot, and then go back. Then you have En An star An. Okay, the minus sign, minus En An star An. Okay, that's nice. So these two terms clearly cancel. This minus sign cancels and leaves us with summation over n En An star T An of T. Okay, that's the Hamiltonian. It's a sum of infinite number of terms, and each term is En An star An. Okay, that's the Hamiltonian we have found, and as we wanted, we have expressed everything now in terms of the dynamical variables An. We are still at the classical level. Everything is classical. My action is classical. Hamiltonian is classical. These are not operators. Now I want to quantize this theory. I want to make a quantum theory out of it. So let's quantize. And recall what we need to do quantization. I promote A to an operator, of course, A star or complex conjugation to Hermitian conjugate, okay, and that's it. There is nothing. Of course, we have to impose the competition relation, but of course, the P also becomes an operator, and then I impose, maybe not here, impose the competition relations which we talked in the previous lecture. Okay, so that is what we have to do. Okay, and let's see. So if I look at the competition relation, let's see what we get. Competition relation. So A and P, if I take An of T and Pm of T, okay, and calculate its competition relation, this will be I h bar times the Poisson bracket, and Poisson bracket has to be 1 because these are, or delta mn, because these are canonically conjugate pairs. So I get I h bar, that's the prescription, right? That's the prescription of making quantum theory. Okay, so this is what I have. This delta mn is coming from the Poisson bracket. Now something, let's see what PM was. So I go back. PM is I h bar an star, or PM is I h bar am star, which becomes am dagger. So I h bar am dagger. That I h bar factor I can pull out, it comes out of the commutator. So you have I h bar an of t, and you have am dagger of t is I h bar delta mn, and the factors of I h bar cancel on both the sides. Okay, these you can cancel. So I can cancel them. Okay, and you get the commutator between a and am dagger to be delta mn. Okay, that is good. And what is our Hamiltonian now in the quantum theory? So the Hamiltonian of this system, okay, this quantum mechanical system which we have found by quantizing the classical action whose classical equations of motion are Schrodinger equation, that Hamiltonian H is now summation over n en an dagger an, right? So the Hamiltonian is, let me write on the next page. So the Hamiltonian of the theory is an dagger an of t. Okay, let's check. Perfect. And remember what is En? En are the eigenvalues of small h. Okay, that's what En is. So that is the Hamiltonian of the theory, and we see that this is something familiar, right? This is, if you look at the each term, like let's take the first term E1 A1 dagger A1. Okay, that's the Hamiltonian of a harmonic oscillator which has its frequency as E1. Okay, or so that's the harmonic oscillator that you have. And what we see here is that your system is a sum of infinite number of harmonic oscillators, okay, because n runs from 1 to infinity. Okay, so the quantum mechanical system that we have got is a collection of harmonic oscillators, an infinite number of them. Okay, and these harmonic oscillators are not talking to each other. You see, there is no coupling between A1 and A2. There are no cross terms in this. So it's completely diagonal. Okay, so there is no interaction between one oscillator and another oscillator. So all these oscillators are completely free, and this is a free theory. Okay, the system that I am showing to you is a free theory, despite the fact that we started with the potential term in the original action, or the Schrodinger equation had a potential. Okay, so let's stop here. Let me just write down an infinite collection of harmonic oscillators. Okay, and then there is no interaction, so this is a free theory. Okay, we'll continue further in the next video.